my bit of the show is trying to look at how the different factors pull together to make buildings low carbon, possibly zero carbon. That's the human factors and of course the physical factors. So start off with, what is zero carbon, and anybody who's been involved in this will know it's many different things. An idea of how much energy we use domestically, what renewables can do. When you actually see this, you may think that I'm very opposed to renewables. I'm not. I love renewables. I have them myself, but it's not perhaps everything it might be. Building out energy wastage. So what is it that we can do to the building fabric to stop energy being wasted? And then of course the contribution of the occupants. What is it the occupants have to do? Do they have to do anything, or do they suddenly go low carbon just by being in a building where everybody else has done the work? So when I started writing this, I was thinking, well, zero carbon, what does that mean? Does that mean that there's no carbon being used in the construction? All that embodied energy in the bricks, the bulldozers, all the rest of it? Maybe. Maybe it's the maintenance when things start to go wrong. We've got an old house and things are always going wrong, and there's a lot of carbon used in trying to put them right. Or maybe it's the operation, how you live in it, or maybe it's decommissioning. When you come to the end of the life of the building, are you going to tear it down in a zero carbon kind of way? And so there are a huge number of carbon inputs there, but I thought maybe what we should do is just do it simply, and so pull back and ignore the indirect energy costs, ignore the construction, ignore the operation and maintenance, and of course ignore the huge amount of carbon that's embodied in the goods that we purchase and use in the building, the water that's brought in, the cornflakes you eat, and all the rest of it. I've also put in some assumptions here that the grid is going to remain pretty fossil fuel dependent, and so we can't look upon grid electricity as zero carbon by any means. And the stat I love for this is that 27 countries in the EU, and Britain is only exceeded by Malta and Luxembourg in the paucity of our use of renewable energy. So I've proposed here that biomass is not infinite. Those guys who are involved in the big biomass plants and shipping in wood chip from Brazil and indeed from Scandinavia may well have a view on this, but it seems to me we might run out of trees if we started making biomass the fuel of the future. And I've assumed that heat pumps are broadly as fossil fuel efficient as mains gas for heating, because essentially a heat pump will return you 3 parts heat for 1 part electricity, and a thermal power plant will take 3 parts heat to produce 1 part electricity. So they sort of balance out. And my last thing is looking at what do we mean by net energy usage. So obviously if you've got renewables and they're based on solar and that kind of stuff, you're going to get a lot more in summer than in winter. So I'm not assuming this building is off grid. I'm saying if we put in all of the energy, if we net it out over the year, the energy that the building uses and that the building generates, that it is about zero. And so starting to look at domestic energy usage, I put down as our challenge to reduce energy consumption to the point where demand can be fulfilled using just zero carbon energy. And in order to do this, you need a common currency. So how is it you can compare Chatsworth, which is the top building there, with Nelson Mandela Towers, which is the bottom one? And of course the currency is the number of kilowatt hours, number of units of energy that you use per metre square of the dwelling for a year. And to give you a rough idea, for the average UK dwelling, 100 would represent keeping a single bar electric fire on for the entire year, 24 hours a day. And so that would include everything that you're using for heating, obviously, also for water heating, also for your television, for your cooking, the whole lot. So obviously there are going to be vast differences between big buildings with relatively few people in them, where you'd expect the energy efficiency, the usage to be quite low per square metre, and small ones which are intensively used, where you'd expect it to be quite high. So here's a typical UK home, and I think these figures were 2001. So total usage 23,000 kilowatt hours per year. The average home size is actually going down. It was 87 square meters, but more recently it's come down to 83. And you've got a split there with space heating weighing in at almost two-thirds of the energy use is actually the space heating, which is a huge amount. And you might notice these numbers here, if you can see them, is I think 1971 and 2001. And so if you think that we've suddenly become vastly more energy efficient in our homes, the answer is no, we haven't. So what are our options from renewable energy? This is a great slide which comes from the Merton Rule people. And you can have wind turbines, obviously, and you may be aware of the Warwick wind trials, and if you're interested in wind turbines on domestic premises, it's a very good place to look. Solar thermal, where you're turning solar energy into hot water. Solar PV, photovoltaics, which turns solar energy into electricity. And you could have a ground source heat pump, which I mentioned before, which is a way of turning electricity from outside the building, usually, into heat. And so I put that in blue because in my view, that's not really renewable, because you're using grid electricity, which comes from gas and it comes from coal. Private wire, you could have your own wind turbine on a hill. Or indeed biomass, and again I put that in blue because I'm concerned about the Brazilian rainforests and whether there'll be any left if we get too enthusiastic about it. And last you've got CHP, combined heat and power, and that is that's a way of preventing you from wasting all of the heat which currently our power stations do by setting off great plumes of heat through their cooling towers, so that you actually use the heat and as well as the electricity generated. Question is, how effective are they? Well, the Merton Rule came out in 2002, I think, and a whole series of initiatives have followed that with local councils, local government. Scots has been very good on this, the London plan and so on, where new build developments of a certain size have been required to have a certain percentage, and it does vary, of renewable or low carbon or zero carbon, and the definitions vary, energy. And there was a good study done by London South Bank University in 2007 on the Mayor's London plan, and Croydon and Merton, who were the two first councils to do this, did an analysis in 2009 of all of the places which had put in renewable resources to run their buildings. The data was really very poor, and so only about a third of the building operators gave back reasonable figures, and these figures were projections, not what actually happened in use. And so what came out very clearly was the most popular, i.e. residential ones, were zero carbon, solar thermal, photovoltaics, and to a certain extent heat pumps, but the most carbon effective were non-renewables. So they were combined heat and power and combined cycle heat and power. So you've got an immediate mismatch there between the number of things that people are putting in and their effectiveness. If you put all these things together, how much can renewables do? I've taken three studies here. Viridian, who actually manufacture solar thermal equipment, have put in a study, PV Compare, which is a really good study from Oxford, which looks at various technologies, and the Warwick wind trials looking at wind. And so these are well-constructed studies, and they tend to be on the positive side. And I could go and bore you to death on what these numbers mean in detail, but just to give you a view, they come in, it seems to me, at about 25 kilowatt hours per metre squared per year. So that represents about 9% of the requirement of that 2001 home we saw before. So if you like, if we were just going to rely upon these, we would have to find 91% of our savings from somewhere else. which really brings you on to wastage. So how do you build out wastage? What are those things that the building designer can do? Well, passive house is a big thing on the continent. Well, big in terms of what we do in the UK, but there are only 20,000 of these things, and they are draft-proof, it's super insulated. They've got low energy lighting, low energy appliances. They are optimized so you get lots of sun through the windows, so that you get lots of solar gain, and they are really, really efficient places. And indeed, they work for retrofits too. That there is a small market of quite expensive retrofits, but they undoubtedly work. So this is a place in Austria. And pre-renovation, they were using 192 units just for space heating, and post-renovation, they were using 14. So a spectacular success. But the cost was 640 euros per square meter. So it comes at a price. So looking at effectiveness, this gives you 4 models. There's the standard UK dwelling on the top left, 2001. This is 280, which we looked at before. Passive house standard, it was 120, and that's a pretty good advance, because there's no loss in quality of life in these places. That's fine. Bottom left is Bed which you probably know as the in South London, in Beddington. Comes in at an average of 82, and Hockessin, which is in Nottinghamshire, comes in at 26. So you've got a huge variety there, and different ways of skinning the cat. And this is Hockessin, and Hockessin, so far as I'm aware, and probably there are people in the audience who can tell me otherwise, is the only significant development that has actually achieved and retained zero carbon status in the UK. And if you look on the left, you can see that they have these massive sort of atria, which bring in a whole lot of solar energy, which is stored in the tiles below and in the bricks on the right, and they open and close the windows to moderate the heat flows in and out of the building. And they've got a big lake in front of them, and on top of them they've got photovoltaics. And of course they actually have 2 wind turbines out there, 2 5-kilowatt wind turbines, which work reasonably efficiently, and they provide just about enough energy to run this. It will strike you that if you're going back to Nelson Mandela Towers, the chances of getting so much photovoltaics on your building, adapting your atria, and putting up 5-kilowatt wind turbines would be more limited. But if you're going to do this, kind of thing, you have to have some kind of adaptation. So the people who are in Hockessin are enthusiasts. They are people who love low energy living. That's why they're there. And to a certain extent, they compete to see how little energy they can use. So they're not probably exactly the same as your average Joe in the street. And so these numbers are actually taken from Bed because I didn't have them for Hockessin. And so there's a winter satisfaction in, I think, 2007. And so the white is I'm totally comfortable. Anything slightly pink is I'm getting a bit hot. Anything slightly too dark blue is I'm getting quite cold. So in winter you'll see that people are getting pretty cold in Bed but they're prepared to make a compromise here. And in summer they're getting really quite hot. So we have we're used to being able to moderate temperature very well with fossil fuel based systems. In these instances, you have to make a compromise. You have to move away from that and say, I'm prepared to sacrifice myself at a certain level for the greater good. So there's this trade-off of personal comfort against altruism, and to a certain extent against economy. How much money am I going to save? And those tend to trade off in temperature on one side, your thermal comfort, but also in your use of appliances. Are you going to have a 48-inch television, for example? Are you going to run the washing machine all day? All of these things have an impact when you get down to these very low energy buildings, which you have to be at if it's going to have any chance of becoming zero carbon. And it requires some active engagement with the building. So if you remember Hockessin, a couple of slides back, they have those wonderful hot atria, but you need to open windows and close the windows right. Otherwise you boil yourself in summer and you freeze yourself in winter. And you have to be committed to it in order to make it work. And they actually have some good stats on their website if you're interested, which show what happens when you go wrong. And if you think it's good to have 36 degrees of heat in your bedroom, this is not comfortable stuff. And of course, the last thing is the rebound effect, or Jevons paradox. Jevons was a Victorian guy who did a study on the use of coal, and he said, as we use coal more efficiently, so we use more of it. And the thought is, as you use your energy more efficiently in the building, you then compensate by going on your EasyJet flight or whatever. And that is a big, big, big factor. So you can't just look at the energy in the home, you have to look at the energy per person. So what's the occupant contribution? That emotional thing, that investment that you'll make as a human being to try and make this building work. Well, this is also from BedZ, and on the left you can see the owner occupancy. What I mean is the ownership of the building. So that on the extreme left, the first one is the average, and the next three look at who owns the building. So the biggest one is in social ownership. The next one is in mixed ownership, and the third one is in private ownership. And when I first looked at these things, I said to myself, well, it's obvious, isn't it? You know, people who don't own the building don't care about the building, and therefore they use more energy. But in fact, that's complete rubbish. Because if you have a look at the one on here, this is actually based on the size, and so that one there, sorry, is the smaller home, and it goes down. Sorry, yeah, is the smaller home going down to the larger home. But there are some big anomalies in there. So you have an average house at the bottom here. This is maximum variance. The heat, they are using 0.4 kilowatt hours per person per day, up to 2.2. So what's that, 5 times? More than 5 times? Nearly 6 times. And power between 1.1 and 10.9 kilowatt hours per person per day. Now, some of that is because people are in the buildings differently. You know, they may be out at work all day, all that kind of stuff. But an awful lot of it is how you react as a human being, and whether you care, whether you're engaged with the building. So, in conclusion, it's a pretty big challenge. Our issue in this country is spectacularly heat wastage, and this last winter proved it pretty well, I think. You can improve the building fabric pretty easily. We've got Passif House, we've got various models over here, regrettably very few of them, but we can prove that we can squeeze that energy down fantastically well. You can eliminate almost all of that wastage. And you can put on your on-site renewables. But your on-site renewables are really quite small. With the best will in the world, your on-site renewables, as they are at the moment, are not going to sustain the life that we have become used to. And lastly, this proves, I hope, that like at Hockerton, you can go genuinely zero carbon now. But you have to have people who are deeply committed to it, properly engineered buildings, and a big space to stick up wind turbines. Thank you.